All right, so I just got done making a video about this paper, and I was trying to upload it, so I looked at the open review page, and I read the first review, and I just thought I had to show you this. Now, before you see the review of the paper, but just look at this review. So the paper is about optimizer grafting. It's about transferring the learning rate of one optimizer to another optimizer. It has some experiments in it and proposes this algorithm to investigate sort of learning rate schedules. Okay, main review, S1, which I guess is strength 1. A large amount of experiments is conducted and plenty of results shown in the appendix. Okay, S2, a novel optimizing mode of grafting two different optimizers is proposed. Got it. So you know a little bit about what's in the paper. Weakness 1. The paper structure is strange. I recommend to read some published proceedings to try to make this paper more clearly. What? Just to say, these are accomplished researchers, right? That are the authors of this paper. I actually show who the authors are. The structure is strange. I recommend reading. Read a bit. Maybe a book. Maybe you'll learn something. Weakness 2. Some format may not be legal. Okay. Weakness 3. The theory is not reasonable. By the way, the paper proposes no theory. The theory is not reasonable. In other words, you just tell me you do it like this, but not why it's reasonable. Okay, I mean that is a even though the paper explains clearly why they do everything, that might be a criticism, like you haven't really given a theoretical foundation for your reason. But then, actually, I don't think Adam grafted onto SGD, so this is the new method they propose, it's SGD with the learning rate of Adam. Actually, I don't think Adam grafted onto SGD will be better than Adam. Notice this is what they show in the paper, that they make experiments to show that this is the case. And it's not like this person has tried it out and has said, it doesn't work for me, or it doesn't work in this other paper. No. The entire thing that this person says is, I don't think this will happen. No reason. What? Why? What is this? This is a type of reviewers that people have to fight with. And then there's like some hubbity. I'm sorry, if they show in the paper that this is the case, then either you claim they are lying or you have conflicting evidence or anything like this. But simply sitting here saying, I don't think so. What? I mean, then we why? This is why. I'm confused. In my view, this method is more like an SGD with multiplying a large constant to its gradient. I mean, at the end, that's what it is. But like, has this person actually read the paper? Weakness 4. I have a question. That's a weakness. A weakness is I have a question. How to compute the norms? How to compute these norms? It's norms. Like the paper clearly, like they don't say it's L2 norms, but they clearly, how do you compute the norm of a vector? Is this calculated with this is answered in the paper. This is clearly answered throughout the paper. If not, figure 1 is a wrong example. Well, it is. So how is it a weakness if you have a question that is answered in the paper? And then weakness 5. The results shown in tables are not strong enough. Right? A large amount of experiment is conducted and plenty of result is shown in the appendix. The result shown is not strong enough. Well, what do you mean not strong enough? Like not highly performant enough? Because that's not what the paper's about. Not strong enough, you mean not enough? Because, well, the other reviews, it's not like the other reviews are necessarily good reviews of the paper, but at least they have some criticism like, hey, you're not theoretically motivated or something like this, and they are a bit extensive, but like this is it's I guess, if you're some company researcher and so on, your bonus might depend on a submission being accepted or not, which, you know, if you're at Google or so, I mean, you're doing well, right? But if you're like a PhD student and you need to get papers accepted within a certain amount of years, and then I don't think that what you clearly show in the paper is the way it is, because I just pull it like somewhere out of here. Okay, enough of me ranting. Let's go into the paper. By the way, I make one mistake. I make one mistake in the paper, which is kind of similar to what the person is here. So there is a diagram, and I'm just gonna describe it right here, where I say there's an arrow like this and an arrow like this, and I say, well, the combined update step would be something like in between, which is not the case. It would be actually one of the arrows just rescaled. Errata. Okay. Bye. Last thing. This is the best. I forgot. Confidence. You are absolutely certain about your assessment. This is the highest score. This is the reviewer rating themselves. You are very familiar with the related work and checked the math and or other details. Really? Because here it says, I'm confused and I have a question. The following is a community-inspired paper review, which means that we have talked about this paper in our Discord paper discussions. We do this regularly, and I can take a lot of good opinions from there and bring them into my videos. If you're interested in joining these paper discussions, join our Discord and watch the events channel. Hi there. Today we're going to look at a paper by Naman Agarwal, Rohan Anil, Elad Hassan, Tomer Koren, and Cyril Chung, but it is not the paper that you see right here. See, this paper is called Disentangling Adaptive Gradient Methods from Learning Rates, and it's on archive with the authors. Now, allow me to present this paper right here under review at iClear with anonymous authors. That's called Learning Rate Grafting, Transferability of Optimizer Tuning. Now, suspiciously, the two papers have pretty much exactly the same content, so, you know, safe to assume that we might make an educated guess about who these authors might be. I'm going to review the obviously newer version, because newer is always better. So, what is this paper about? This paper is about a technique called learning rate grafting. And grafting means that we transfer the learning rate from one optimizer to another optimizer. They have a bit of a graphic right here. So what we would do is we would take two different optimizers and think of things like SGD or Adam or something like this. So these are fairly popular optimizers in deep learning. We would take one of them, and that one would give us the information of what the direction of updates of our weight is. So let's actually say SGD here is this purple one in this direction. You can see that will follow in general the direction that SGD tells us to go. However, we don't go exactly what SGD, we don't do what SGD tells us to do. Instead of, we take the learning step size or the learning rate from Adam and we go that far. So one algorithm dictates where we go, the other algorithm dictates how far we go. And what this does is it implicitly transfers the learning rate schedule from one optimizer to another optimizer. And as a result of this, many things happen. So one simple thing that results from this is we're able to investigate some of the differences between the optimizers. Surprisingly, one of the things that this paper finds is that maybe the different optimizers, it's a bit let's say over-described, over-hyped what the differences really are between them. A lot of times it simply comes down to the learning rate schedule that the optimizers induce. And as soon as you transfer that to another optimizer, the other optimizer will perform just as well. So the differences between a lot of these optimizers might just come down to the learning rate schedule. Another thing that they can do is they can, for example, transfer these learning rate adaptations that one does to the other, and that makes it in practice, that gives you benefits in practice. For example, Adam. Let's look at Adam. Adam maintains 3 buffers for every single parameter. So let's go SGD. SGD, for every parameter W, it has 1. It essentially just updates that parameter. If you have SGD with momentum, then you also have the momentum parameter that it maintains. So for every parameter, there is a momentum parameter, and then as a gradient comes in, it updates the momentum parameter, and that it uses that to update the weights. So 1 buffer essentially per parameter that we want to treat. Adam, on the other hand, maintains like 3 buffers. I don't exactly remember what they all are, but they are like the squared sums of gradients, and then they are somehow the current gradient squared, or some exponential moving average across that. In any case, it maintains like 3 different buffers per parameter. And that also means that it has like at least double or 3 times the memory requirements of SGD, right? SGD, even with momentum, needs a lot less memory than Adam. And that's a big deal, because memory is one of the things that, especially on GPUs, is a limited commodity. So if you're able to reduce the amount of memory that your optimizers need, then that means that you can train bigger models, because now you have a bunch of free space. So what this grafting method allows you to do is it allows you to essentially run SGD adjusted for the learning rate schedule of Adam, but without having to run Adam. You can simply transfer the learning rate schedule or the adjustments to the learning rate from Adam to SGD, and that's a pretty cool thing. So we're gonna go look into how this paper does it, what it suggests, and it's a pretty straightforward paper. I think it's pretty short, pretty cool to read, and yeah. So what exactly is grafting? They first do a little bit of an excursion into preliminaries, and that essentially presents these adaptive optimizer, these adaptive methods. So if you look at SGD, what it does is pure plain SGD, its update rule, which they characterize as an algorithm A right here, that takes in the current weights of the neural network or whatever system you optimize, and the current gradient, right? So W are the weights, G is the gradient, both at time step t. It will output for the next weight. So A always gives you WT plus 1. It will output the current weight minus a step size times the gradient. This is classic gradient descent. Now this right here is a learning rate schedule. So even in gradient descent, people do learning rate schedules. Sometimes there is a bit of a warm-up, and then you might reduce it over time. Maybe after some epochs, might go down and so on. Or you might not, right? But these are usually handcrafted learning rate schedules. Now, when you go to other things, such as Adam or AdaGrad or anything like this, of all of these, AdaGrad is probably the most simple. So the reasoning behind AdaGrad is the following. If you have a loss landscape, which we're going to draw here as some sort of a topological plot, so every line is sort of a same loss height, and this is the global optimum right here. So you start out somewhere here, you calculate the gradient maybe goes in this direction, so that's the local tangent to these iso lines. That's pretty simple, right? You see, you go straight here. Even if you have some sort of a bit of a mistake at the beginning because it's stochastic, you can see in general you go downhill. However, what if the landscape doesn't look like this, but it actually looks, like really skewed in one of the dimensions? So it's really steep in one of the dimensions, and it's really flat in the other dimension. Now what happens here is that if you start off the same thing, maybe you have a little bit of noise, you tend to make, if you do this step, so if you look at this, what you're going to do is probably you're going to make a big step into this, and then it's really steep, right? Now it's really steep into this direction, so you're going to bounce over here like really far, and then it's really steep in that direction, so you're going to bounce over here really far. So because it's so steep in that direction, you're going to bounce around with way too big of a step size, just because one direction, this direction, is way steeper than this direction. So what do methods like AdaGrad do? AdaGrad flattens out this landscape by observing. I mean, the algorithm doesn't see the landscape, it only sees these points where you're at and the corresponding gradients. So what AdaGrad does is it simply says, I'm going to look at one of these gradient steps, right? Let's say I'm here. This is my gradient here. I'm going to look at what's the change in this direction, what's the change in this direction, and then I'm going to normalize by it. So the update rule for AdaGrad is something like Wt plus 1 equals Wt minus some step size times the gradient. But now the gradient gets scaled by the sum of square gradients and the square root of that. So what this means is that I'll take all of the gradients that I've seen so far, I square them, and then I sum them all up. And in essence, this is element-wise, by the way. So these are vectors, and we are talking about diagonal AdaGrad. So in essence, what this says is that if I have my gradient vector here, I'll put a matrix in front of it, and every entry in this matrix is 1 divided by the square of the gradients I've seen so far. So it's a bit of a normalization. If my gradients in this particular direction were really large, I'll divide by a lot. If my gradients were really small, I'll divide by just a little bit. So you can see that it transforms a landscape like this to implicitly look much, much more well-conditioned. And you can even see, because we have a total sum right here that goes on with time, that there is a little bit of even a decreasing learning rate built in, because the square is always positive. So we're simply going to add on to these buffers, and that means that we are going to decrease our learning rate implicitly over time. So here you can see two things. You can see that these preconditioners, they have their reasons for existing, first of all, but much more important, they introduce an implicit learning rate schedule, right? This thing right here is an implicit learning rate schedule. And all of these algorithms like AdaGrad, Adam, and so on, they introduce exactly that. So this part right here, that's the implicit learning rate schedule. And we're now wondering, so how much of the success of these optimizers comes from the fact that they do something like this right here, where they look at each of the coordinates and they adapt with respect to how steep they are and so on, and how much simply comes from the fact that they say, well, now you need to go far, now you need to go not so far, now you need to make a big step, now you need to make a small step. So that's what we're wondering. And grafting allows us to answer these questions. So in grafting, what we do is we leave the optimizers as they are. So here we would leave SGD to do SGD, right? So again, we're at the start here. I'm running out of colors to draw over top of one another. Let's go with green. We're at the start right here, and we want to, and let's say we've made this step. Now we want to go into this direction, right? SGD would make a big jump right here. And AdaGrad or Adam maybe would do two things. It would say, well, since this one direction is very steep, I'm not going to make that big of a step into that direction. I maybe make a smaller step, and I also adjust my direction. And what grafting does is it says, okay, we're going to take your suggestion of how far we should go, but we're still going to go into the same direction that we originally went. So we're taking the step size that the one optimizer suggests, and we'll transfer it onto the direction of another optimizer. So this allows us to answer the question, what's really important here? The step size schedule or the direction, the particular direction that these optimizers produce? And the answer is going to be the step size. So the grafting algorithm is detailed here. This is the simple version, which is, I believe, called global grafting. So you can see we're going to note, we're going to take this right here, this notation. So M stands for magnitude algorithm, I guess. I don't know. I've invented it. D stands for direction algorithm, and M hash D is the combined grafted algorithm. So what we're going to do is we're going to feed the same input, the current weight and the current gradient, to both of the algorithms. They will manage their states, internal states, independently, but yet they will not yet update the weights. They will simply suggest each an update. What we'll then do is we'll look at two quantities, this right here and this right here. So this is the step that this here is WT plus 1 according to algorithm M, and this is WT plus 1 according to algorithm D. And we're going to look at both of the steps that they would suggest, right? If we subtract this here, this is what step do you suggest? And then what we do is we compute the norms of these steps, and we'll simply normalize the quantity of D right here by the ratio of these norms. If we rewrite this a little bit, you can see much more clearly what's going on. This is WT plus, and then I'll write the norm, the first norm here, WM minus WT, and then I'll write the second thing, WD minus WT divided by the norm of WD minus WT. Oops, norm. So there you can see that we'll take the direction, we'll take the direction of the D optimizer, and we take the direction because by dividing by its norm, we normalize it. So this always has length 1, right? So this is simply the direction of the step that the D optimizer would do. And we multiply it by the norm of the step that the M optimizer would do. Notice M only comes in here through this norm, so M has no influence on the direction that we go, while D has no influence on the magnitude of the step, because we always divide by its own magnitude. So that's the grafting algorithm. And they have some properties right here. You can graft an algorithm onto itself. It won't do anything. You can graft multiple algorithms and so on. It's not commutative, yada, yada, yada. It's not necessarily a descent method, which is interesting, but I guess irrelevant because I consider that an edge case. And now they have one more trick up their sleeve, how they make it more interesting. Namely, this is what they call global grafting, where it's just one global learning rate, right? These whole norms here, they are just one number at the end. Okay? They can also do this, for example, for each layer individually. So they divide up the parameters into layers and then do it for each layer individually. If they were to do it for each parameter individually, right, then it would not have any effect. So if they do it for each parameter individually, I think it would just revert to being the old, it would just revert to being the M algorithm, right? That's what they say right here. If they do it for each parameter individually, they might as well just run M, because the magnitude of each parameter is dictated fully by M, and we don't calculate the direction of D because each of the entries is separately divided by itself, so D will just output a bunch of 1s. So yeah, that's the reason, and because the norms are just of size 1. In any case, that's a bit of pushing it to the limit. We can either do this globally, or we can do it for each layer individually. That's this partition parameter right here. So what does this, where does this go? What they try is, notice that we're still in the case where we need to run both algorithms simultaneously, right? So for each step, we're here. For each step, we have to consult SGD, what would you do? And then Adam, what would you do? And then we do the grafting between the two things. And then we maybe get this direction right here. We go on, we again ask both optimizers, we go on. In the experiments, they do a good job of controlling for the actual compute that they give to these experiments, and therefore you can make some assumptions. But one worrying thing about me, just as a side note, is that Adam has this, for example, this internal state, right? So it has these, it accumulates the gradient into buffers and so on, yet we make an update step that is not into the direction that these buffers would suggest. So technically these buffers are wrong for the path that we're taking. The buffers expected that we're going to take this path right here. And I'm not sure how much we actually miss due to that. I also don't know how we easily would correct it, but I would just wanted to say that the internal state is updated as if we were to actually take the step that the algorithm suggests. However, we're not going to take that step at the end. So this is a bit of a shady practice in this grafting algorithm. In any case, as we do run both at the same time, you can see right here, so there's an experiment where experiment for implicit hyperparameter transfer, comparing hyperparameter search for SGD with momentum versus grafting with, and then M is SGD, so it's Adam grafted onto SGD. Is that true? M, because it seems like D is SGD, right? It's always M hash D, and then SGD is at the end. Huh. Well, maybe that's wrong. I don't know. As the way I understand it is that you have the trials with SGD, you have trial with Adam, which is in blue right here. And then if you take this grafting approach and you do Adam along with SGD, so you do the direction of SGD, but the step size that Adam would do, you see that you almost get the same performance. Right? In fact, in this particular case, SGD with the Adam step size even outperforms Adam like a tiny little bit. If you go to a higher batch size, that's no longer the case, but also here you see that it seems to be that as soon as you get this step size right, not only can you not match it with any humanly chosen, let's say, step size of SGD, which would be all the gray stuff, but also immediately most of the, or all of the benefits of the Adam optimizer versus SGD vanish. So it really seems to be a thing of the step size. And as far as I understand it, that's the global grafting. Yeah, they do make some, like they mention a bunch of times that this number right here, no, it's layer-wise, sorry. It's layer-wise grafting. They mention a bunch of times that this is higher than just using Adam, but I'm not sure how exactly robust this is, especially as you see here, if you go to the higher batch sizes, it is a different story. They also do some experiments with ResNets, which aren't as cool, like they're not as performant. So here you see a lot of the times that they take SGD, which is a good algorithm for these types of problems. By the way, SGD was a bad algorithm for BERT. That's why they used it as the direction and grafted the learning rate onto it. In these particular cases, SGD is actually pretty good, and so is Adam, as you can see right here. And the other algorithms AdaGrad seems to be kinda bad. If they now graft SGD or Adam onto AdaGrad, which you can see here with the layer-wise or the global grafting, it helps a little bit, right, compared to just AdaGrad, but it's not like that it really gets into a highly performant region. So I guess the conclusions of this is that sometimes, or is that the step size schedule is an important parameter. It is part of why some of the optimization algorithms outperform others. It might not be all of the reason. I guess that's a cautious thing you can say right here. They go into a little bit of analysis, for example, about this giving you sort of new insights. So, for example, people have come up with this yellow learning rate schedule for SGD. There's a bit of a warm-up, and then there is just a decay after every few epochs and so on. And if you transfer that to AdaGrad, so if you graft that on AdaGrad, right? The trick is we don't transfer it. We don't simply say, well, these are the steps. We ask both optimizers, and then the resulting learning rate schedule might be a different one from either of the two. And the cool thing is that here, the algorithm seems to really decide kind of on this polynomial warm-up for AdaGrad before then using this decay that comes from SGD. So it's pretty neat that it allows you to kind of gain an insight into what these algorithms are doing. They do a last thing right here where they say, can we get away with not running both algorithms at the same time? And that's what they do right here. So what is this? They take AdaGrad and they take Adam and they take SGD and they run it for just 2,000 steps. This is very small number of steps, let's say, in training of BERT. So these is just the first few iterations. They run both. And what they do is they observe the norm ratio during grafting. So they do this grafting where they run both and they observe the ratio of norms between what one and what the other one would suggest. Okay. So essentially they do this grafting and they observe how the step sizes between the two relate. And then they say, okay, we'll just take the median over these 2,000 steps, and that is going to be our learning rate correction to SGD. So essentially we're saying we're going for 2,000 steps. How does the learning rate of the implicit step size of Adam compare to SGD over these steps? Maybe it's always 10 times higher for some layers. Maybe it's 50 times higher for other layers. You can see they split this up into different layer types like embeddings or self-attention and so on. And then they say, well, okay, so from here on out, let's just run SGD, only SGD, but always correct the step size by this ratio. And that actually works, apparently. So I don't think there's a plot necessarily right here, but you can see this is one of the results. So with Adam, you again get this 69.5. SGD is way worse because this is BERT. But then the combination, as far as I understand it, that is this discovered per layer learning rate correction. So that's one number per layer. Even then, SGD is better if you have this learning rate correction given by Adam than just Adam itself. A little bit, but still it is. Or is it not? No, this is grafted, sorry. I think this is the one. This here is the one where they keep it constant. And that is not better, but it is at least, it is the same, right? Like, I hope the rounding was in their favor right here. Otherwise, they'd have like added added like one digit and could claim that they're better. But in any case, it's pretty cool to see that the performance here jumps by quite a bit, and it's not that much worse as if you had executed Adam alongside, right? That's the 70.1. On the bottom here, they have different kind of even more quantizations, which make the result worse most often, but it seems like if you get them exactly correct, then it can improve by a little bit. I'm not too big of a fan of these kinds of things. It shows that you can go simpler, but yeah, you have to kind of hit it exactly right with this hyperparameter, and that defeats the purpose a little bit. In any case, I think this is two powerful things from this paper. First of all, this can be used for investigating these optimizers, right? Because you can now see, aha, here is the exact effect that the step size schedule is having on one or the other optimizer. You can sort of mix the step size from one with the directional update rule of another one. The second one is that something like this, where you simply quickly observe how two optimizers stack up against each other, match each other in the step sizes they would suggest. Maybe you need a little bit more memory at the beginning because you execute both of them. However, you only need to do this for a few number of steps before you can then go ahead and simply take what you learned and save a whole bunch of memory, because as they do right here, they only, from here on out, they only execute SGD. No more Adam. The ratios are fixed and they are per layer. So that's pretty cool and pretty powerful. Especially, I'm wondering how these things generalize. So can I take the ratios of one network and transfer them to another one with a slightly different architecture, maybe a bigger network or a different problem, a different data set? So this seems to be a pretty exciting future direction, because it makes everything a lot more efficient if we simply know that, embedding layer, okay, let's just multiply that by 50 or something like this. And then lastly, this is a bit of my worry, is that I don't know where we go if what I said right here, the internal state of the optimizer assumes we're taking a certain step, yet we take a different step. I don't know how that influences the entire grafting algorithm. They have a lengthy appendix if you want to go into that, of a lot of different results right here, and but I don't want to go into that right here. In the conclusion, they say we've introduced grafting, a binary operation which blends the behavior of two optimization algorithms towards investigating the entanglements between widely used adaptive preconditioning rules and learning rate schedules. Yada, yada, yada. Furthermore, we have shown that grafting can be used to extract standalone learning rate corrections, enabling us to train a transformer using SGD with momentum for the first time. Well, I guess people have been able to train them before, just not to satisfactory accuracies. We hope that this finding will simulate further empirical research, power of simple per layer learning rate schedules. Okie dokie. The empirical phenomena examined in this work seem to be unexplained by current theory. That is also an interesting point. We hope that the experiments enabled by grafting will aid in developing more robust beliefs about both adaptive methods and learning rate schedules, and guide future theoretical inquiry. All right, theory people, here's something for you to explain. All right, I hope you have enjoyed this overview of learning rate grafting. Sorry for de-anonymizing the paper right away, but yeah, that's a bit silly anyway. In any case, if you like this, hit subscribe, smash like, get enough sleep, and I'll see you next time. Bye-bye.